So thanks everyone for tuning in. Today we have Viktor Jahnke, who's currently in Korea, who's going to tell us about his work with Willy Fischler and Juan Pedraza on the chaos and entanglement spreading in gauge theory. So Viktor, thanks a lot, and take it away.
Oh, okay. Thank you very much for the introduction, and thank you for the opportunity to present this work. Okay, so I hope you guys enjoy it. So let me get started. So this work was done in collaboration with Willy Fischler and Juan Pedraza. Okay, so this is an overview of my presentation. After some short introduction, I would like to discuss a little bit about quantum chaos, and then briefly review how quantum chaos can be described in the framework of holography. And then finally, I will discuss some bounds on chaos and whether these bounds are violated or not in a non-commutative geometry. Okay, so the basic question that I would like to answer is the following. Holographic systems are maximally chaotic, and they saturate a set of bounds on the spread of quantum information. And we basically would like to answer the question of whether non-locality can affect these bounds. For instance, can non-locality violate, for instance, the bound on chaos, the bound on the Lyapunov exponent? This is the type of question that we would like to answer. And to answer that question, we study chaos in a prototypical example of non-commutative theory, which is n equals 4 super Young mules defined in this non-commutative geometry. So because this non-commutative geometry is known to display non-local effects. Okay, so that so far so good. This is the okay, good. Okay, so let me briefly review a few aspects of classical chaos, then go to quantum chaos. And I would like to focus more on the conceptual aspects of this type of calculations. And so let me start with this idea of classical chaos. So if we consider some classical trajectory in phase space, the idea of classical chaos is that if I change a little bit the initial condition, I create another trajectory, and the distance between these two trajectories increases exponentially with time. So here, lambda is the classical Lyapunov exponent. Okay, so in the quantum case, as I'm measuring the sensitivity dependence on initial conditions, I would like to compute this derivative. So this can be written in terms of a Poisson bracket. So when we write things like that, it's kind of easy to go to the quantum case. We just replace the Poisson bracket by the commutator. Okay, so generically to diagnose chaos, one considers the expectation value of this and also the square of this to avoid phase cancellations. And in more generically, one replaces these Q and P operators by two generic Hermitian operators and diagnoses chaos with this quantity here, which goes by the name, some people call it double commutator. So I will call this the double commutator. Okay, so this is the quantity that is supposed to diagnose chaos. Okay, so let me explain how precisely this diagnoses chaos. So this quantity can be written as a sum of 4 terms. And just for simplicity, I will consider the case where V and W are Hermitian operators, which are also unitary. So V square and W square are 1. So in this expression, the first line just gives me 2. So 1 comes from this first term and 1 comes from the second term. So the time dependence of this quantity, the non-trivial time dependence, comes from the terms on the second line. Okay, so for a chaotic system, one expects this type of behavior for this double commutator, some kind of growth and a saturation to a constant value, which in this case equals 2. It's kind of small here, but okay, so for this quantity to approach 2 at later times, that means that the terms in the second line should approach 0 at later times. So I call it here these terms on the second line. The picture here is the blue picture representing the terms in the second line, and I call these terms out of time order correlators. Okay, so this is how these quantities are supposed to behave if the system is chaotic. The double commutator approaches a constant value, and the out of time order correlator goes to 0 at later times. So the important time scale here is this so-called scrambling time. Okay, now I would like to try to give you some physical picture for this behavior, just to have a more clear qualitative understanding of this. So here there's we have a cartoon of scrambling. So initially, let's say I have these two operators, V and W, and initially they involve like separate degrees of freedom. So this ball here is supposed to represent the space of degrees of freedom. So initially, the two states, the two operators involve different degrees of freedom of the system. But as the time goes by, this operator W essentially expands in the space of degrees of freedom. And as this operator expands, this double commutator grows. And eventually, this operator gets scrambled among all the degrees of freedom of the system. At this point, the double commutator saturates to a constant value. And as I told you before, this basically implies that the out-of-time order correlators need to go to 0. So this is a picture for scrambling. Basically, the idea that you perturb the system, the perturbation initially involves just a few degrees of freedom, but this perturbation kind of mixes among all the degrees of freedom of the system. Okay, so just this happens in this time scale, which is called the scrambling time. Okay, so this is just to have a picture, understanding for the concept of scrambling. And I would like now to try to give you some sort of physical explanation of why in a chaotic system, the out-of-time order correlator goes to 0 at later times. So the basic idea here, just for convenience, I'm considering the operator W at time minus t instead of t. This I am doing this because it will be easier to compare this with black hole physics. And the idea here is to see this out-of-time order correlator as an overlap between an out state and an in state. Okay, so this is the in state and this is the out state. Okay, so in these pictures that I will describe in the following, I will represent the thermal state with this cat beta, and this beta will be just a straight line. So, okay, so let me start constructing by constructing this in state. So this in state is basically the operators, the two operators acting on the thermal state. So I start with this line here, in which V acts on beta. So I will think about this state as a fine-tuned state that displays some perturbation at time equals 0. So if I evolve the system backwards in time, I expect this perturbation not to be there. It kind of thermalizes backwards in time. But the idea here is that you have a thermal state, and at time equal to 0, this thermal state displays some fluctuation, which you can measure with this operator V. So, okay, so I start with this state and I go backwards in time. If I go forwards in time, I expect this fluctuation to rematerialize at time equal to 0. Okay, now I will do something different. I go backwards in time, and before I go forwards in time, I apply this perturbation W, which is a different operator. And the question now is, what happens when I go forward in time? Before, when I didn't have this W operator here, these time evolution operators cancel and I recover the initial state. But the claim here is that for a chaotic system, this perturbation W kind of destroys the fine tuning and the perturbation V fails to rematerialize at time equal to 0. So this will be the essential idea of chaos. The idea that I have this initial state, and if I go back in time and perturb a little bit the system, when I go back to the future, I do not recover the initial condition. So this will be the essential idea. Is that clear? Or?
Yeah. So I have a question before we move on. So I understand that if you want to make contact with black holes, it's natural to consider a thermal state. But I mean, this chaos is gonna be. It seems to be both a property of a theory, so like Hamiltonian, as well as the state that you consider, right? So like over here.
Yeah, that's true.
So to what extent it's been understood how the choice of a state affects this physics?
So sorry, what's the question again?
To what effect it has been understood if the choice of state affects the findings? So for example, if these Lyapunov exponents depend on the choice of the initial state.
Okay. So so you can have chaos. Basically, the chaos can be either like you might have like a complicated Hamiltonian that displays chaos, or you can have like a simple Hamiltonian, but you have a thermal state. You have contact with a thermal bath. But in this case, like in the case that I will consider, which is chaos in the context of holography, I will always think about chaos as a result of a thermal system. And in this case, the Lyapunov exponent, it's always like 2 pi times temperature. So it's basically the fact that you are in a thermal state that produces chaos. But unfortunately, I'm not sure if I can give you an answer for how this depends on the state. But in this particular setup, it's a result of the fact that you are dealing with a thermal state, basically. So I'm going to restrict to this case, but I'm not sure if I answered your question.
Well, I'm not sure much is known, but thanks for elaborating on it. Thank you.
Yeah. The short answer is that I don't really know, but yeah. So I'm gonna restrict to the cases of chaos in thermal systems because I'm gonna think about black holes.
Sure. Let's move on.
Sorry. Yeah. Sure. Okay. So if you think about the out state. The out state, you start with beta, then you evolve backwards in time, you apply the operator W, and then you go forwards in time, and in the end, you apply the perturbation V. So in this state, in this representation, this state by construction displays the perturbation V at time equals 0. So it's clear that the out state is kind of different from the in state. So from this perspective, it seems natural that the overlap is 0 or is small, at least is small. So is that clear? Like this second?
I think so, yeah.
Yeah, so this should be contrasted. In the case of integrable system or a system which is not chaotic, one expects this small perturbation in the past. One expects that this perturbation will not have a large effect on the system, especially if it involves different degrees of freedom. So in an integrable system, one expects this V perturbation at least partially rematerialize. So in an integrable system, this final state here will not be so different from this final state here. So for this integrable system, this overlap will not be precisely 0. So, okay, so this is just to give you some general picture. And the basic idea that one should keep in mind is that you have an initial state, which displays a perturbation. You go backwards in time, you perturb a little bit, and when you go back to the future, you don't recover the initial condition. That's the picture you have to keep in mind. Okay, so For future reference, I should say that when you consider local operators, this this double commutator is expected to have this form, at least for some systems. Like for holographic systems, you always get this form, and for SUIK and also for some spin chains. But this is not like so generic. You have different types of behaviors for this double commutator. But what I would like to emphasize here is that now the operators are local operators, so they are separated in space, and this introduces this spatial dependence in the double commutator, and essentially the quantity that controls the behavior of this operator in this case is this so-called butterfly velocity. And this butterfly velocity essentially describes some kind of effective light cone inside which this double commutator is of order 1. So here in this picture, I have the light cone. And even inside light cone, this quantity, due to scrambling, due to this delay in scrambling, this quantity is not expected to be very large. But this quantity will only have an order 1 value inside this so-called butterfly effect cone or something like that. Okay, so this is like some kind of emergent light cone that appears in chaos, and this will be important later. Okay, so now I would like to describe these things in the context of gauge gravity duality. So I wasn't sure if I should assume familiarity with gauge gravity duality, or should I briefly review this? Should I?
No, I think it's fine without.
Okay, so I just want to emphasize something, that sometimes people describe chaos in the bulk. So they put some string, and they discuss the chaotic behavior of this string or of this particle in the bulk. Here, the philosophy is different. Like, we are discussing chaos in the boundary theory. And this will be, of course, this will have a description in the bulk, but it's chaos in the boundary, just to be clear. Because sometimes people discuss classical chaos in the bulk. And here we are going to discuss quantum chaos in the boundary. Okay, so as I told you before, the chaotic behavior will be basically due to the fact that we are dealing with a thermal system, and this is related to the fact that we have a black hole in the bulk. So, okay, so here is just some review. I just want to say that we are going to consider these local operators acting on the boundary. And whenever you act with a local operator in the boundary, you create some field excitation in the bulk. And I will refer to this field excitation as a particle. So I will consider like operators such that I have like some one particle state in the bulk. And of course, the thermalization in the boundary theory has this nice description in the bulk in terms of a particle that is falling into the black hole. Okay, so now I would like to try to describe chaos in terms of black hole physics. So here, this picture is supposed to represent, like in gray here is the black hole interior, and the boundary is supposed to be represented by this straight line here. So here in the left, I'm basically representing a state that displays this fluctuation V at some particular time. So this can be represented in the bulk. Like whenever you act with this operator, you create a particle in the bulk. But you can imagine that you follow this particle forwards, let's say backwards in time. And you can imagine that you have like a time-independent Hamiltonian in which you have like a fine-tuned state that displays this perturbation at some particular time. So in this particular interpretation, you can see the bulk picture for this will be in terms of a particle that escapes from the black hole, reaches the boundary, and then falls back to the black hole. Okay, so in this picture, it's kind of clear. It's kind of nice to see the dependence on initial conditions, because in the right here, if I act with some local operator W in the boundary, this W operator creates a particle in the bulk. And if the time separation between these two operators is large enough, this particle will be falling into the black hole for a very long time. So this particle will have a very large blue shift, and it will have a very large energy, and it will basically increase the black hole size a little bit whenever it crosses the horizon. So in this particular situation, it could be that the V particle here fails to escape from this larger black hole, and the V particle never materializes in the boundary. So this would be like the bulk picture for this picture that I showed you before. Okay, so a small perturbation in the past destroy your initial condition in the future. So is that picture clear? Okay, so I guess so. Okay, so this is a qualitative picture. I will be like, I try to be a little bit more precise about this. So I will consider this thermofield double state, which is due to a two-sided black hole. So this has the interpretation in terms of wormhole geometry. And for future reference, I will say that this is a fine-tuned state, because if you consider the time cosine slice here of this geometry, the left and the right boundaries have local correlations. Okay, so I'm saying this is just for future reference. Okay, so let me try to be a little bit more precise on how to describe chaos within the framework of two-sided black holes. Basically, the basic idea is that I will not have like time to explain in full details how to compute the out of time autocorrelator. But the basic idea is that this operator here is due to some particle in the bulk. Here I draw a light-like particle just for simplicity. But if I move this operator at some early time, this will basically generate, we'll have like a particle that is falling in the black hole for a very long time. This particle will have a very large blue shift. And this particle basically generates a shockwave geometry. And this shockwave geometry, it's actually very simple if this perturbation is early enough, because basically it divides the space-time into regions, which are basically the same as before. And the basic prescription that one has to follow is that whatever crosses this shockwave suffers a no shift in one of the no directions. So if this is the unperturbed metric, the shockwave metric it's given by this formula, and it's a very simple formula, and it's essentially described by this function h, which is the shockwave profile, and it can be argued that the double commutator, or it's essentially proportional to this shockwave profile. So within the framework of this gravity iconal approximation, one makes this identification. So essentially, and this shockwave profile satisfies some simple equation in the bulk, which has this solution. So this is the basically holographic result for the double commutator, and it's characterized basically by three parameters, which are the Lyapunov exponent, the scrambling time, and the butterfly velocity. And all these parameters are given in terms of the geometry very close to the black hole's horizon. Okay, so this is like the standard way of extracting the chaotic properties of the boundary theory using the holographic framework.
So before yes? Can you elaborate a bit like on the origin of T star and butterfly velocity from this?
Oh, sure. So basically, okay, so this quantity here is actually proportional to you have like the Einstein's equation here, okay?
Yeah.
So at some point you have the G Newton here, the Newton constant.
Oh, okay.
Because this is in the right side of Einstein. So this G Newton, I replace it by T star.
Okay.
So basically here this is G Newton. Instead of Bekenstein-Hawking entropy, I could have written just like 1 over G Newton.
Okay.
So this is the origin of this T star. And this time dependence here, the origin is that basically if you consider that you have essentially here you have 2 particles in the bulk, and if you take into account the time difference between the 2 boundary operators, you eventually will find out that this factor here is essentially proportional to the center of the energy in the center of mass square, and this energy increases exponentially with the time separation between the 2 operators. So this is how you get the right hand side. And okay, so the butterfly velocity here, it's basically, you can see that this butterfly velocity is essentially given by 2 pi over beta divided by this mass. And this mass is not the mass of the field, it's actually, I call it a mass, but it's just a function of the metric functions at the horizon. So it's not the actual mass of some field.
Okay.
So if you consider like these PP solutions in ADS, you have basically the same equation without this mass, because these PP solutions are constructed in the context where there's no black hole. So this mass is 0 if there is no black hole, because this mass, I think it turned out to be proportional to some metric function, some R minus RH, and it goes to 0 at if the horizon is 0. Okay, so I'm not sure, was that?
I think that's fine. Yeah, thank you.
Okay, so sorry, I should have elaborated more on this, like, but anyhow, like the reference that explains this very nicely is this one, Schenker-Stanford. It's a string effect in scrambling, and unfortunately, I didn't make a very good job explaining this. I just put the results. But okay, so this is a way to diagnose chaos, considering these local shock waves. There is yet another way of diagnosing chaos in holography, which is based on the mutual information between regions on the 2 sides of this black hole. So before I describe the results that we get, let me briefly summarize how to diagnose chaos using the mutual information. I know it's kind of confusing because it might be too much information, but I think it's just like 3 slides. So okay, so the mutual information is this quantity. Basically here, the mutual information between A and B is given by this formula, where S of A is the entanglement entropy of region A, and so on. And this quantity essentially provides a bound for correlations between operators defined on the regions A and B. So here I will choose A to be a region on the left side of the geometry, and B will be a region on the right side of the geometry, and in this thermofield double state. So I will basically be interested in these correlations, this left-right correlations. And this is a good measure because this quantity provides an upper bound for correlations. Okay, so to compute these entanglement entropies, in holography, we use this Ryo-Takaya-Nag prescription. So here, this picture on the left is supposed to represent a 2-sided black hole. So you have here the left boundary, the right boundary. Here's the horizon. So this is supposed to represent the t=0 slice of a 2-sided black hole. So let's say here I have region A, and on the other side I have region B. So to compute the entanglement entropy S of A or S of B, I basically need to compute using the Ryo-Takanagi prescription, I basically have to compute this the area of these blue curves here, okay? So the entanglement entropies of A and B are easy to compute, and the entanglement entropy of the region A union B, for this entanglement entropy, I have basically two options. I could consider the area of the blue curves or the area of the red curves, but I have to choose the one which has the smallest area. So if I consider a situation in which the red curves has the smallest area, I will have a positive mutual information, as you can see here in this last equation. So I will start in a situation in which these regions are big enough such that the red curves has the smallest area. So in this particular situation, I will start with a positive mutual information. Okay, so this is the unperturbed geometry. So the fact that this unperturbed geometry has a positive mutual information between these large regions is basically showing you that this thermofield double state has special correlations between the left and the right boundary. And so in that sense, this thermofield double state is a fine-tuned state because it has these delicate correlations, at least at time equal to 0. Okay, so now I will consider how this mutual information changes as we add a shock wave to the system. In this picture, when I add a shock wave in the past, what this makes is basically increases the size of the wormhole. So if the size of the wormhole depends essentially on how far in the past is the shock wave. As I move the shock wave in the past, the blue shift becomes larger and larger, and the wormhole becomes bigger and bigger. So you can see that when I introduce the shock wave, basically the area of these red curves increases. So the mutual information decreases and eventually drops to 0 if the perturbation is early enough. So this disruption of the mutual information by perturbations in the asymptotic past is an additional way of diagnosing chaos. Basically because you have these special delicate correlations at time equal to 0, and you perturb the system a little bit in the past, and you observe that you no longer have these special correlations. But it's maybe more clear to see that if we take into account that this mutual information provides a boundary for AB correlations. So let me go back here just for a second. Like here in this equation, you can see that let's consider a simple case in which these one-point functions are 0. So if I say that the mutual information is 0, I'm basically saying that these 2-point functions between A and B is 0. Okay, so in this situation, if these 2-point functions are 0 in a shockwave geometry, that means that the shockwave geometry is basically obtained by acting with some operator in the thermofield double state. So this 2-point function in this expectation value in a shockwave geometry is actually a 4-point function, where you have operators you have like 3 operators in the right boundary and A in the left boundary. So the fact that the mutual information drops to 0 in this configuration where the wormhole becomes bigger essentially implies that out-of-time order correlators also go to 0. So this secretly encodes out-of-time order correlator. And this is, of course, this is a different type of out-of-time order correlator because you have some operators in the right boundary, some operators in the left boundary. But this out-of-time order correlator is related by analytic continuation to one-sided out-of-time order correlators. So is that more or less clear, or is it still confusing?
I think it's okay.
I think it's okay. Okay, so far so good. Okay, so basically this is the other way to diagnose chaos using the mutual information. So you have these two approaches. In this case, you consider like homogeneous shock waves, and in the first case, you consider local shock waves, and they are two complementary ways to diagnose chaos. Okay, so let me briefly mention some bounds on chaos. So for a system with a large number of degrees of freedom, there is a sharp bound on chaos, which is basically set by the temperature. So this is very specific for thermal systems. Okay, so there's also some bounds for the butterfly velocity and also for this so-called entanglement velocity, which I will introduce in a second. So basically, one can, using arguments based on causality, one can derive bounds for both for the butterfly velocity and for the entanglement velocity. And the third bound here is actually a conjecture, and it basically states that this entanglement velocity should be smaller than the butterfly velocity. So the question that we would like to answer is how non-commutativity affects these bounds. So basically, if the theory displays non-local effects, we would like to answer. We would like to know whether these quantities can capture these non-local effects. So my collaborators, sorry.
I have like a very stupid question. So like the first two bounds, I'm like I understand that C is equal to 1. So like in what sense? I mean, apparently they are non-trivial because they come from papers written recently, right? It's like what's non-trivial about them? I mean, why they're non-trivial? Why they're not guaranteed by causality?
I know, yeah, because yes, because this butterfly velocity, some people like argue that this butterfly velocity or this entanglement velocity. Actually, let me talk about the butterfly velocity first. Some people argue that this could define some kind of bulk, bulk causality should be defined by this butterfly velocity, but it's not actually obvious because when you look at the form of the commutator, like let me go back here. The butterfly velocity, it's basically you have if the two operators are separated in space, you have some exponential suppression due to spatial separation, and but the effect, the commutator also grows with time. So this interplay between decrease with space and increase with time, you can define this notion of some velocity. But it's not clear that this is actual physical velocity, that something is propagating with this velocity. So
you say that a priori it could be bigger than the speed of light according to this.
Yeah, so people don't actually know, but it's also kind of weird because in some relativistic system you expect the effective velocities to be the velocity speed of light, right? So it's kind of weird that you have this this butterfly velocity, which is generically smaller than the speed of light. And some people say that this actually you're considering a thermal system. So in the thermal system, you're just considering a subset of the Hilbert space. So you don't actually have access to all the states in the Hilbert space, only a subset of the Hilbert space. And this butterfly velocity should define some effective velocity in the subset of the Hilbert space, which will be like generically smaller. But people don't have a very clear picture, like what this velocity represents up to this point. So using some alternative definition for this butterfly velocity, like this, it's basically depends on you have to assume an asymptotically ADS geometry and use no energy condition, and you can show this bound to be true. And here, for instance, the entanglement velocity, the physical interpretation, it's like, I think it's even worse, like it's not clear what this velocity represents. And here you have to use, basically use positivity of mutual information to show this. But yeah, so it turned out to, the physical interpretation of these quantities, it's not absolutely clear. So that's why it's not obvious. But like, this is a kind of expected, but it's not like trivial. Okay, so I should say this holds like this. The derivation of these bounds basically assume Lorentz invariance, and for the first bound here, the derivation assumes ADS geometry, asymptotically ADS geometry. So you're basically you need to have that asymptotically ADS geometry means that you have a relativistic boundary theory. Okay, so to investigate these bounds, we consider this prototypical example of a non-commutative theory, which is this n equals 4 super Young-Mills theory living in this non-commutative geometry. Okay, so I'm not an expert on non-commutative geometry. My collaborators are the experts on this setup. But essentially, you have like, this is basically the theory that lives in the word volume of D branes, in which you have non-zero B fields in the Neveu-Schwarz sector. So the metric it's given by this formula here. This is the metric in Einstein frame. And so basically the parameter that controls the non-commutativity is this theta. And this theta appears in the metric in this function h, and appears through this quantity a, which is basically proportional to the square root of theta. And lambda here is the 't Hooft coupling. Okay, so so this is the metric. So this system has some subtleties which you have to properly take into account. For instance, there are no gauge invariant operators in position space, basically because the non-commutativity of the space mixes with gauge transformations. But so in this case, we cannot perturb the boundary theory with local operators. But it's possible to define gauge invariant operators in momentum space. So instead of using the usual formula for the out-of-time ordered correlator, we actually consider the double commutator in momentum space. And it's interesting that this double commutator in momentum space, you can extract the Lyapunov exponent and the butterfly velocity as a pole of this quantity. This quantity has a pole precisely at this point. And I will not go into the details, but the definition of entanglement entropy for non-commutative theories is also subtle, but there is a proposal by Fischler. And anyhow, so this is like some subtleties that we have to take into account. Basically, the same procedure, we cannot apply the usual procedure to extract the chaotic properties of the boundary theory, but we can more or less do the same thing if we work in momentum space. Okay, so let me now show you the results. First of all, despite of this non-locality, the Lyapunov exponent saturates the chaos bound in this system. And this happens, basically, it should happen actually. We should know this from the beginning because the non-locality affects the scrambling in the physical space. But the Lyapunov exponent is related to the scrambling in the matrix degrees of freedom. So if I want to scramble a region, like in this picture, a region of size R, the time to scramble this region, it's basically, I have to scramble each cell, and I have to propagate through space. So the time is given by this formula. So T star here is the scrambling time, is the time to scramble each cell. And here is the additional time due to spatial separation. So the scrambling time, it's basically related to the scrambling in the matrix degrees of freedom of these gauge theories. So this is why the fact that we have a non-commutative geometry does not affect the Lyapunov exponent. Okay, so is that more or less here? Okay, so let me move on. So the results for the butterfly velocity, we have basically, we have non-commutativity basically between two coordinates, but x1 is like a commutative direction. So we have like a commutative plane that goes along with x1, and we have the non-commutative plane. And what we observe is that in the commutative plane, the butterfly velocity doesn't change. It's not affected by the non-commutativity. So this is basically the result that one gets for the commutative version of n equals 4 super Yang-Mills, which is also the result for instance, for a CFT in the dimensions. This is the butterfly velocity. For d equals 4, this formula gives 2/3, which is the result that we get here, like the result for the butterfly velocity for a 4-dimensional CFT. In the commutative plane, the result is affected by the non-commutative parameter through this function a. And I should say this is wrong in our paper. In the first version, the two butterfly velocities are affected by the non-commutative parameter. But this is, okay, so but I will correct that in the next version. But one does not expect the velocity, I mean, like one expects the velocity to increase in the non-commutative plane because you have no local effects in the non-commutative planes, but one does not expect anything different in the commutative plane. So this is, unfortunately, it's wrong in the first version of the paper. And anyhow, what we observe here is that along the non-commutative plane, this butterfly velocity can even becomes bigger than the speed of light. And this is not a surprise since the system displays no local effects because of this non-commutative geometry. So, but it's kind of nice to see that the butterfly velocity actually captures this effect because this is not obvious from the start. It's not clear if this quantity is really useful as a diagnose of causality in the boundary theory.
So a quick question, because like over here, like we're just staring at this plot as a function of a times the horizon radius, but yeah. I mean it's always possible that the gravitational solution displays some sickness, some problems for some values of parameters, right? And the question is like, shall we trust like all the values of a times the horizon radius that you display as being physically viable?
Yeah, I think that's a good question, and that's like the third thing that comes to my mind was like maybe I should restrict the parameter, right, to consider like small values of a in such a way that there is no violation of causality. But so yeah, so according to my collaborators like Pedraza and Fischler, they say no, this should happen. That you should have like a superluminal butterfly velocity. But yeah, so in principle, you could say, okay, this is a pathology, and then maybe I should restrict the values of A. But like this, in other calculations for this system, this parameter is not constrained. Like at least people don't constrain like using this kind of causality arguments. So at least according to them, there is no reason to restrict this. Like this could take any value, and in principle, the solution is not pathological for large values of A. The only thing is that the solution kind of deviates from an asymptotically ADS geometry. So basically, this is a result from the fact this superluminal butterfly velocity results from the fact that you have a non-asymptotically ADS geometry produced by this parameter. But yeah, so I'm not so sure. Like maybe we should restrict the value. So yeah, so maybe you're right, but yeah, so I'm not so sure. Yeah.
Okay, let's move on. There's not much time, but thank you.
Thank you. Okay, so now let me show you. I told you before that the mutual information is also a useful diagnose of chaos. So let me show you some plots for the mutual information. So the mutual information is it's plotted here on the right, and in the left I have basically some complementary information, which is the entanglement entropy of A union B, which is the non-trivial part. So basically what we observe is that if we start with some positive mutual information, if you introduce a shock wave in the geometry, this mutual information drops to 0. And here the non-commutative parameter is 0 in the right, and the non-commutative parameter increases as we move to the left. So we see that the non-commutative parameter basically, sorry?
No, there were no questions.
Ah, okay. So basically the non-commutative parameter makes the mutual information drop to 0 faster. And it's interesting to observe the behavior of this entanglement entropy of A union B, because it's kind of complementary, because this quantity is basically a constant minus this. And we can see that there is some region in which this entanglement entropy increases linearly with time, shockwave time, and it saturates to a thermal valley. So this is very similar to the behavior observed in global quenches, studied by Maldacena, Hartman, also by Liu and Su in this entanglement tsunami story. So this is this picture, let's say this shockwave geometries. I think they kind of provide an additional example of a quench protocol in which you can study the time dependence of entanglement entropies. Okay, so in the last line here, I say that, okay, so there is a linear behavior close to the saturation. And this linear behavior, it's essentially described by this so-called entanglement velocity. So this quantity appears in this context of variation of entanglement entropy. So it does not have a very clear physical interpretation. But as I told you, it has been shown by Cassini, Liu, and Marc Mezet that this quantity should be bounded by the speed of light. And what we observe here, it's pretty much the same that we observe for the butterfly velocity. If you consider regions in the commutative plane, regions like I have regions A and B. If the region, I consider basically strip-like regions. So if the strip is the finite part of the strip is contained in the commutative plane, I get basically the result that I would get for n equals 4 Soubry-Yang Mills. So there is no, the non-commutative parameter does not affect things in the commutative plane, but it does affect the entanglement velocity in the non-commutative plane. So the formula is complicated, so I will not show the formula to you, but we can see that pretty much like in the case of the butterfly velocity, we can have superluminal entanglement velocities. And as you said, maybe this means that we should restrict the value of these parameters, but maybe it's just a way that this quantity is telling you that you do have non-local effects in the non-commutative directions, because basically this bounds for the entanglement velocity, it basically assumes Lorentz invariance. And this non-commutative parameter explicitly breaks Lorentz invariance. So if you do not have Lorentz invariance, you don't expect this to be bounded by the speed of light. Okay, so I guess pretty much this is all the results. I should say, like, what I think is interesting is that both these quantities kind of capture these non-local effects of the boundary theory. And there's still yet another bound, which is this bound, that says that the entanglement velocity is smaller than the butterfly velocity. And this bound is still valid in our setup. So maybe this is like a very general bound, because valid even in non-local systems. I should say also that these quantities, dB and VE, they have like some interpretation in terms of propagation of quantum information. So it's okay. So let me move on. So okay. So it would be interesting to test further this conjecture in other non-local theories, other examples of non-commutative geometries, or maybe Lipschitz geometries. And it would be desirable to compute these out of time order correlators in a non-commutative field theory using perturbation theory and compare these results with strong coupling results. So I guess this is all I have to say. Thank you for your attention.
Okay, thank you, Victor. We have quite a number of questions, but maybe we have some more.
Okay.
Well, no more questions here. I think myself I also exhausted like.
So was that like more or less clear, like the explanation for chaos?
That's fine. Thank you. Yeah. We can still ask like if there are questions from people online. But I guess not. Okay. So in this case, thanks again. We're gonna